for our day 5 notes today, we are talking about our key features of functions, which this is a topic we've talked a lot about. I think you'll find a lot of this stuff is very familiar to you. So what we have over here is the function f of x. We don't know the equation of it. They're just calling it f of x. Is graphed over here on the right. They want us to find the following questions. So first, they want us to state the y-intercept. You guys know the y-intercept. That's where our graph crosses your y-axis. So our y-intercept is right here at positive 2. Next, they want us to state the x-intercept of the function. So our x-intercepts, we actually have 2 of them. We have them one here. So that's at 1, 2, 3, 4, 5, 6. X is negative 6. And then we have another one at 1, 2, 3, 4, where x is positive 4. What is the alternative name that we give the x-intercepts? We have a couple of other names that we use for them. We call them roots, or we call them zeros. Reason being is because this is when the function itself is equal to 0. Because if you remember, this is your x-axis. That's when your y equals 0, so your function equals 0 at that point in time. All right, our next one, over the interval of negative 1 to 2, is the function increasing or decreasing? So I'm going to go to where x is negative 1. Here's where my function is. If I follow it all the way to where x is 2, my pen is going up the entire time that I follow my function. So that tells me that this is increasing over the interval negative 1 is less than x is less than 2. I find, again, increasing, that's when you guys, you know when it's increasing, you just don't always know how to tell me the interval part of it. So that's what we have to practice. D, give the interval over which the function is greater than 0. What is a quick way of seeing this visually? So the function's greater than 0. That means you're looking for when the function is positive, because positive numbers are greater than 0. So what we do is we look for when are we above the x-axis. That's when we're positive, because that is when your y values are positive. So that means the function is positive at that point in time. So it's positive from here, and then it goes up and down and up and down, but still, even while it's going up and down, it's still positive. It's still above your x-axis, and it stops right here at 4. So it's positive from negative 6 is less than x is less than 4. That's never going to be equal to, because it's not positive when it's on the x-axis. It's 0 right here. And 0 is neutral. It's neither positive nor negative. Same thing over here. It's a 0, so it's not positive or negative. That's why we don't have the or equal to signs here. Other part of the question, what is a quick way of seeing this visually? It's above the x-axis. That's how we see it visually, and that's what we did to help us find the answer. Okay, next part. Part E. State all the x-coordinates of the relative maximums and relative minimums. Label each. Okay, so this is something I know we talked a little bit about in 9th grade, but we didn't specifically talk about it too much. We have our relative maximums, and then if you look at the next question, it's talking about absolute maximums and absolute minimums. So relative maximums just means that there's a point in time where the graph gets higher and then it goes back down, but it's not the absolute highest it can possibly go. So for example, our graph right here, this would be a relative maximum, because our graph comes up and it goes back down, so it's a high point, but it's not the highest point that we have in our graph. Same thing with over here. This is another relative max. Because again, it's a high point, but it's not the highest point. So for our relative maxes, our x-coordinates would be 1, 2, 3, 4, negative 4. And then for our other one, it's at 1, 2, 3, 4, 5, positive 6. And that's where our two relative maxes are. So let's find our relative mins. So again, it's a low point, but it's not the lowest point. It's like we got one right here. That's a relative min. And we got another one right here. That's a relative, min. So these happen where x is -1 and where 1, 2, 3, 4, 5, x is 5. So those are our relative ones. Again, they're just a high-low point, but they're not the highest and lowest points. So for our absolutes, up here would be our absolute max. There's nothing higher than that point, and there will never be anything higher than that point. And this is our absolute minimum. There's nothing lower than that point. There will be nothing will ever be lower than that point. So for our absolute max, our x-coordinate would be, oh wait, what are the, oh no, here they want us to give us the full value. They don't want just the x-coordinates. So our absolute maximum is at 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So it's at 2, 8. Our absolute minimum is at 1, 2, 3, 4, 5, 6, 7, -8, -4. There we go. So those are our absolute max, absolute mins. Part G, state the domain and range using interval notation. Well, I'm going to hold off on the interval notation for right now. We're going to do that on our next page of notes. So our domain, so what you have to remember with your domain, those are your x values. So our x values go from here to here. And there's everything in between. So this is from -8 to +6. So our domain is -8 less than or equal to x less than or equal to 6. These ones are or equal to because those points are included. Those are little closed circles up there. So then our range, remember those are your y values. We got to find our lowest, which is right here, to our highest, which is right there. So this goes from -4 to +8 for our range. So that's -4 is less than or equal to y is less than or equal to 8. And then h, if a second function, g of x, is defined by the formula 1/2 x plus 2, what is the y-intercept of g? Well, I can see this is almost in a form we're used to, our slope-intercept form, y equals mx plus b. So what I'm going to do is I'm going to distribute my 1/2. And I get 1/2 x plus 1. Now this is our mx plus b form, so which means our y-intercept is that part right there. So the y-intercept of g would be 1. Other way is you could have graphed that up here on the graph if you wanted to, but you didn't have to for that. Okay, let's go to our next one. So here is all of our notes, key features. So these are all terms you have been through before. X-intercept, y-intercept, increasing, decreasing, a constant, positive, negative, zero, absolute max, absolute min, and behaviors, all that stuff. You've been through this before. If you are still struggling on this, you need to go to Quizlet and be practicing your vocabulary. You need to know what these words mean. A couple of new ones would be, however, continuous. If we have a continuous graph, that means you can graph it without lifting your pencil. Another way to think of it is that there are no breaks in the graph. That's another way some people define it. No breaks in graph. So it just continuously flows. So a little example over here of a continuous graph would be like that. That is a continuous graph. I was able to draw the whole thing without taking my pencil off of the paper. A discontinuous graph has breaks in the graph. You've seen graphs like this before. An example of what that would look like is you could have a piece here, and then it hops down to here. You got something there. So there's like different sections to the graph. There's breaks. You can't continuously draw it while you're trying to do that. Okay. Even functions. Even functions are symmetric over the y-axis. So for example, one even function that you guys are very familiar with would be your quadratic. It is perfectly symmetrical over your y-axis here. If you were to flip it over, it would be exactly the same function. So that's an even function. Our odd functions are symmetric through the origin. Now, I wasn't going to write over, but I want the word through. Symmetric through the origin. We really haven't done too much with odd functions. But an example of an odd function would be the equation y equals x. If I reflect that through the origin, I would get the same exact line. So those are our even and odds. And as I do this, I just remembered, I had a little brain fart moment. Back here on the first page, because I'm recording these a little out of order, we have done our interval notation. So let's go over that quickly for a second on this problem, on our interval notation on that first page. Because these have the or equal to, remember our interval notations would have the brackets because you include those values. So our interval notation for our domain would be -8, 6. Our interval notation for your range would be bracket -4 to +8, and then close your bracket. So just to clear that up. All right, let's go to our last one. Okay, so symmetry can be used to help sketch graphs. You can use half the points. Symmetry can occur with your y-axis, your x-axis, and your origin. Note, if an equation is symmetric with the x-axis, it's not actually a function. For example, that graph has symmetry over the x-axis. However, if you do your vertical line test, it would fail the vertical line test. This is not actually a function. So that's why we don't usually talk about that with our functions. We deal with our evens and our odds, which go through your y-axis and your origin. So some ways to test for an even or odd function is if you replace x with -x and you get the same exact y values, your function is even. For an odd function, if you replace x with -x and you get the negation of your y values, like instead of a 1 you get -1, instead of a 5 you get -5, that means it's an odd function. So what we're doing first is we have these three graphs. They want us to determine is it even, odd, or neither. So as I was saying on the last page, a function is even if it's symmetric over the y-axis. So this graph here is symmetric over the y-axis. So this one would be an even. For our second one here, if I look at my y-axis, if I try to flip it over, my graph would go that way. So it's not symmetric over the y-axis. If I try to reflect it through the origin, it would be somewhere down there. So it's not an odd function. So this one would be neither. And then our third one again, if I look with my y-axis and I try to reflect it, it's not going to be even. For my origin, one way to tell with the origin, you kind of want to stick a pen in there and you can kind of picture rotating the graph 180 degrees, it's the same as reflecting through the origin, if you remember that from geometry. So if we do that, this graph ends up being an odd function because it's exactly the same when you reflect it through the origin. Okay, so this one, even, odd, or neither. Still trying to figure that out. So this would be an even function if these points were the same. Like 3 would also have to be 3 over here, but it's not. This is 3, this is negative 3. So that's not going to be even. Odd, you would get the negative version, the opposite version. So if I have positive 1, I get a negative 3. Negative 1 should give me the opposite, which it does, which is 3. 2 gives me a 0. Negative 2 gets me a 0. You can't really test that. 0 is neither positive or negative, as we talked about. Positive 3 gives me a 15. Negative 3 gives me a negative 15, so it does negate it. So this would be an odd function. Okay, this one, even, odd, or neither. So let's see here. We got 1, 4, 3, 8, 5, 6, negative 1, 4, negative 3, 8. Because 1 goes to 4 and negative 1 also goes to 4, they give you the same answer. That's your hint that it's going to be even. 3 and negative 3 both go to positive 8. You get the same answer whether you put in the positive version or the negative version of that number. So this would be an even function. All right. That's all we have for our notes today.